Hello, welcome back to Mrs. Ogram's Maths. Today we are going through some worked solutions to a Level 3 Algebra and Complex Numbers parallel paper. So this is a paper that was written to be like the Level 3 external for this standard, but it's not an actual past paper, it's just one that was written to be similar. Okay, so set up in the same way, the same sort of marking applies to it. Okay, so question one, we've got these two complex numbers multiply to make 1 plus 3i over here. And I'm going to use the calculator to do a division to work out the k value in t. So we can do that because if these two things multiply to make 1 plus 13i, then k plus I will be 1 plus 13i divided by 1 plus 3i. Okay, so over to the calculator. In our regular run menu, just a reminder of how we find those options to do complex numbers. So use the option button here and then complex in F3. Okay, so we've got 1 plus 13i divided by 1 plus 3i. Then comparing that 4 plus I with what t is, k plus I, so the k must be 4. Okay, for part B, we've got R values so that this equation has only one solution. That means we're using the discriminant. So we do b squared minus 4ac. That will be equal to 0 when there's only one solution. Okay, so the b value is 6. The a value is r. And the c value is also r. So we get 36 minus 4r squared is 0. Well, 4r squared equals 36. So r squared is 36 divided by 4, which is 9. And r is the square root of 9, so that is plus or minus 3. Don't forget your plus or minus when you're square rooting. Right, for part C, we're on to a merit type of question. So we want to solve this equation. I'm first of all wanting to get rid of the square roots by squaring both sides. So that means that, it will be like this. Okay, so the right-hand side, when I square it, I can just remove the square root. The left-hand side is the place where people will make mistakes because they'll square the individual terms and not square the whole thing. So if we square 3 root x plus 1, I'm going to write that out fully so you can see what I'm doing. So like this, so multiplying out that bracket, we've got 3 root x times 3 root x is 9x. Then we've got 3 root x times 1 and 1 times 3 root x. So that'll be 6 root x. And then 1 times 1. Okay, so then the 9x cancels with the 9x. We have 6 root x will be equal to k minus 1. And just remembering what we need to do, we're solving in terms of k. So we need x equals something with k's. So root x will be k minus 1 over 6, and x equals k minus 1 over 6, all squared. Okay, for part D, we need to work through what this expression will simplify to, and then we're told that the real parts of that expression will be equal to 12. Okay, so let's try put that over a common denominator. So if we do that, it'll be 2 minus I, 2 plus I. So on the k plus ki bit, we need to multiply it by 2 plus I. So we have k plus ki, 2 plus I. And then the k bit needs to be multiplied by the 2 minus I. Then we're going to work through what that means. So on the top, let's expand that bracket. And then the same on the bottom. If we multiply out that, we get 4 minus I squared. Okay, now simplifying. Let's collect together the k terms. So we've got 2k and 2k, which is 4k. We've got 2ki and ki, and then minus ki. So that'll just leave us with 2ki. Then we've got ki squared. Well, I squared is minus 1, so that'll be minus k. On the bottom, we've got 4 minus I squared. Now, I squared is minus 1, so 4 minus minus 1 will be 5. If you're doubting yourself when you're doing this in the exam, of course, you can just type in 4 minus I squared if you just want to double check your negatives and everything, just to, feel a little comfort there. Okay, so now we have 3k plus 2ki all over 5. And we were told that the real part of z is equal to 12. So the real part of this, if we separated that fraction, that'd be 3k over 5 plus 2k over 5i. And the real part would be this bit here. So 3k over 5 equals 12. So k must be 20. All right. Given that w is this, u and v are real constants in these imaginary numbers, we want to prove this. Okay. Okay, so let's start by writing out what this thing would look like on the left. So it'd have 1 plus w squared all over 2 times w. Now I'm not going to expand out that bracket because hopefully some of these bits here will cancel with some of those bits there to try to simplify down to what we were wanting it to be there. Okay, so let's deal with the 1. We want to put that in the same terms as what we've got here. So that'll be the same denominator. So u minus vi squared. If we make that u minus vi squared over u minus vi squared, then that's equivalent. In fact, let's just move that out the way of that question bit there. Let's do that down here. Okay, and then plus the u plus vi squared over u plus vi squared. That will get divided by 2 times u plus vi over u minus vi. Okay, now if we divide, it means we can actually multiply by the reciprocal. So let's change that to a plus, and we'll flip that fraction over. So u minus vi over 2u minus vi. Oh, and I've just realized I put a plus in there. It should have been u minus vi, because the whole point we were doing that was so we could put that bit over a common denominator of u minus vi squared. And then we get u minus vi squared plus u plus vi squared. So what we can do from here is cancel through u minus vi on the bottom here with u minus vi on the top there, so that we then are just timesing by 1 at the top. Okay, so if we expand at the top, we get u squared minus 2uvi plus v squared I squared plus u squared plus 2uvi plus v squared I squared. Then we'll have 2 times u squared plus v squared I squared. Okay, so looking at the top here, the minus 2uvi cancels with the plus, and the v squared, I squared is minus 1, so we get u squared minus v squared plus u squared minus v squared, so that is 2u squared minus v squared. On the bottom we have 2 where the u squared plus v squared, I squared, so I squared is minus 1, so u squared. And I'm really sorry, I've just realized I made a mistake earlier with a transcription error back up here. So when I did this and I flipped that thing over, I turned one of them into a negative when this should have been a positive, so that was a positive, that's positive, and it makes this negative, which will help fix me down here, so that I squared turns the minus v squared into a plus v squared like this. So then the 2 cancels and we get what we wanted to in the first place, u squared minus v squared over u squared plus v squared, as was required in the question. So we are all done. Okay, question number 2. Given that x minus 2 is a factor, find k. So if x minus 2 is a factor, we can put 2 into that expression, like so. And if it's a factor, that will be equal to 0. Right, so 2 cubed is 8 times 3 is 24. Then we've got 4k minus 24 minus 4 is 0. So 4k minus 4 is 0. 4k equals 4, so k equals 1. Okay, for b, modulus means that we do the square root of the real part, which is 6, plus the square root of the, oh, oops, it's not 6, it's 6u. And then the square of the imaginary part. There's no I when you put it into there, you're just taking the coefficients of the real and the imaginary parts there to go into the modulus. That will equal 25. So 36u squared plus 49. Oh, where did I write 24? There we go. 25 squared is 625. So if we square root 16, we get plus or minus 4. And again, don't forget your plus or minus. Okay, so for part C, we're looking at a merit type of question. So we'll write this term here, but replacing z with a plus bi. So z is a plus bi, so the conjugate of z is a minus bi. Z times its conjugate will be a plus bi times a minus bi. Right, let's work that through. So a minus a on the top cancels. We get minus, we get bi minus times a minus makes it plus, giving us 2bi on the top. On the bottom we get a squared minus b squared I squared. So 2bi over a squared plus b squared. Now take a look at that number there. There is no real component to it. It's all times by I. If you wanted to make that super clear, you could do this times by I, so it's entirely imaginary. Or no real component. Okay, find the argument of uv when we have these two complex numbers. I'm just going to draw a little sketch of what that looks like. So on an Argand diagram, because the value here is the same, the k's and the p's, we can plot that out quite easily. So u is going to be positive k in the real direction and negative k in the imaginary. So you've got kk like this. So it's going to look like that. So u, like so. And then similarly for v, we've got minus p and p. So it's going to be negative p in the real direction and positive p in the imaginary. So it's going to look something like this. So p and negative p. So v is over here. Now what we know about that, because it's each of, like if we drew this triangle, that side is the same as that side. So the argument for u, actually let's write that out. So arg of u will be 45 degrees, which is pi by 4, but it's under the axis, so that'll actually be a negative pi by 4. The argument of v will be this way around to that line there, so that will be 3 pi by 4. Then the argument of uv is equal to the argument of u plus the argument of v. That's from de Moivre's theorem. If you're multiplying two complex numbers together, their arguments get added. So then we just have minus pi by 4 plus 3 pi by 4. If you're not great with fractions, just put that into your calculator, but omitting the pi, so you can see what's happening with the fractions like this. And you'll see that that is the same as pi by 2. You could also have looked at that on the diagram. If you see this here, the argument between the two is 90 degrees, or pi by 2. Okay, we're on to locus here, and the clue about what to do with this question is the fact that they're asking for the Cartesian equation, which means that we will let z be equal to x plus iy, so that we can have things in terms of x and y. Okay, so the modulus of z plus 2i then looks like this. And we're just replacing z throughout with x plus iy. Okay, so the modulus of this first one here, so modulus would be x squared plus 2 plus y as the real part squared, but then it got squared for this squared here. So what that does is just simply remove the square root. And then the same on the next one, x squared plus y minus 2 squared. That will all be equal to 10. So let's work this through now. Minus 4y plus 4. Okay, so now we can do some simplifying. So we've got 2x squareds. We've got 2y squareds. Then we've got 4y, and the minus 4y cancels. So we are just left with 8. Okay, so we've got down to the Cartesian equation, and then we need to describe this locus. Okay, so from here you need to recognize that is the equation of a circle. Now, the center of the circle is always given by what is inside of the x part and the y part squared. Well, at the moment there's nothing inside there, so it's actually going to be centered at the origin. And this part here is what gives you the radius. The square root of that is the radius. So the radius is 1. Okay, question 3. For u over v, we are dividing complex numbers in polar form. That means that the modulus gets divided and the argument gets subtracted. So that'll be n cubed over n is n squared, cis 2/3 minus 1/5 will be 7 pi by 15. Okay, for this next one, the modulus of z squared, well, you can write it out in full or you can use your calculator. We've got absolute value here is the same as modulus. So if you did the absolute value of 5 minus 7i, you can put it in like this. So you could do that way and then square it because we want the modulus squared. So it'll look like this. I'm going to show you it worked through so you can see the whole steps as well, but you could just put it into your calculator. So the modulus of that would be the square root of 5 squared plus the minus 7 squared part, but then that whole thing gets squared. So that'll be 25 plus 49, which is 74. 2 times the modulus of w squared is 2 times square root of negative 1 squared plus 6 squared, and that all got squared, so that's 2 times, well, 1 squared is 1, and 36, so 36 plus 1 is 37, double that, you get 74. But if you just prefer to use your calculator, you could have put the whole thing in, show they're both equal to 74. Okay, one of the solutions of this expression is 2 plus I. So we'll call that root number 1. Root number 2 is always its conjugate. Okay, then we can find the other solutions. So we know if this is a root, then z minus that thing is a factor. Same with the conjugate. So that, if we multiply that through, will also be a factor of our original expression. We've got z minus 2 minus I, z minus 2 plus I. Let's multiply that out, we get the following. Let's do the tidying up here, so that cancels, oh, no wait, that cancels with that. 2 i's cancel there. Okay, so we've got z squared minus 4z, and then a plus 4 and a minus I squared, so I squared being minus 1, that's going to become plus 1, so we've got plus 5. Okay, so then if we take a look at what the third factor needs to be to make it equal to the expression. Okay, so for the first term, we see what's happening over here with the 2z cubed. We would need a 2z here. And then for the second part of that factor, you look at what's happening at the end. So for a minus 15, we would have to times the 5 by negative 3. So our third root will be from this bracket here. So if you set that equal to 0, it's going to be 3 over 2. Now for working out b, take a look at the parts of this expansion that would make the z terms. Okay, so for the just z terms, on the left hand side we can do minus 4z times minus 3. So we get this, and then we can also do 5 times 2z, and on the right hand side we have bz. That then becomes 12z plus 10z is bz, or 22z equals bz, so b equals 22. Okay, if z cubed is equal to this thing, we then need to find out m. So let's take a look at what that looks like on an argand diagram. So negative m to the 6i means it's entirely on the imaginary axis, and it's down here in the negatives at negative m to the power of 6. So let's start by writing z cubed in polar form. So the modulus is the length that we have here, which is a length of m to the 6. We don't need it to be negative when it's in polar form because it's a modulus length. Then the argument is this angle here, which is negative pi by 2. So then z will be equal to m6 cis to the negative pi by 2 to the power of a third, so the cubed root of that. We need to find all the possible ones that we have here. We just missed a bracket. Okay. All right, so the first root will be just to simply do that thing to the power of a third. So the modulus times to the power of a third, so m to the 6 cubed root is going to be m squared. And if you're not sure about your powers, when we're doing a power of a power, we times them. So 6 times a third is 2, so we get m squared. And then when we are doing the argument using de Moivre's theorem, the modulus got divided by got cube rooted, and the argument gets divided by 3. So this will be cis of minus pi by 6. Now for the second root, we imagine what z cubed could have started at if we did a whole other circle around. So we could have, instead of stopping there, we could have gone all the way around and back to there again. So that means that it would be the cubed root of m6 cis of negative pi by 2 plus a full circle. And then that will be to the power of 3. To the power of 1/3, cubed rooting it. Okay, so then that is m squared cis of, now that argument started off at negative a half, add on 2, and then divide it by 3. And then the third one, I'm going to do the same again, so m6 cis of negative pi by 2, but we add on 2 circles so that it looks like this. Okay, so m squared cis to negative half plus 4, and then divide it by 3. If we're going to be picky about it, that last one, 7 pi by 6 goes over pi, so it would go like that. And when we're doing argument, we actually turn it into representing it this other way around. So I think you'd still get the marks if you just left it as 7 pi by 6 for most of these, but just for completeness, that's the same as minus 5 pi by 6 if we just take it the other way instead, because we always do arguments between positive pi and negative pi. Okay, so for complex numbers, show that v over u is purely imaginary. Okay, so if we're going to do any sort of working out on modulus and whatnot, that is kind of your clue that we should turn these into Cartesian form. So I'm going to do this. Actually, I'm going to keep the u as a plus b. The v is c plus id. Okay, so starting with the modulus bit, so u plus v modulus is equal to u minus v modulus. Okay, so modulus means we do the square root of the real parts would be a plus c squared, the imaginary would be b plus d squared, is equal to square root of a minus c squared plus b minus d squared. So let's get rid of the square root sign first of all. That's just untidiness. We can just remove that from both sides. Okay, so we have a squared plus 2ac plus c squared, b squared 2bd plus d squared. Oops, plus b squared minus 2bd plus d squared. Okay, so a whole bunch of stuff cancels out there. So a squareds, c squareds, b squareds, and d squareds. And we end up with 2ac plus 2bd, negative 2ac plus 2bd. Oh, no, negative. Okay, so then if we bring the right-hand side over to the left-hand side, we end up with 4ac plus 2b, no, 4bd equals 0, or ac plus bd equals 0. Okay, let's get on with the other part, v divided by u. So v was c plus id over a plus ib. Let's multiply that through by the conjugate of the denominator to rationalize the denominator. Okay, and what do we have coming out of this? Let's go. So AC. Okay, so on the top, that then becomes the real parts are AC plus BD, and then the I parts we've got BC plus ADI, and the bottom is A squared plus B squared. But remember what we had up here, AC plus BD is equal to 0. Therefore, we get V over U is equal to, well, the split zeros out, so BC plus AD over A squared plus B squared I. So it's entirely imaginary.